So let's take a look at 5.9 here. In 5.9, what we're going to do is we're going to look at equations that have fractions involved, similar to what we did in 5.8, but specifically here we're going to look at examples where we have variables as our terms in the denominator. Okay? So we have two optional. I think the other day what we did was method 2. Yeah. So we found the LCD, we multiplied all the fractions by the LCD, and then solved the result of that. Method 1 is finding an LCD for every single fraction in the equation, and then canceling all those LCDs. Because if you divide everything by the same thing, it's like it doesn't have any effect. Right? If I have 5 equals 5, and I divide both sides by 2, I get 5 halves equals 5 halves. Well, that statement is definitely still true. So dividing both sides by 2, we can get rid of that step. So the first method, if you like, if you want to try it, you get an LCD for every single fraction. Make them all the same, and then just cancel them all out, all at once. It's like multiplying through by that LCD. The other day we chose method 2. Okay? So we could try both if you want. So let's look at the example here. How would you go about finding an LCD for something that looks like this? It's not an easy problem at all. This is one where I have to definitely think outside the box. Because factoring is simple, but this is not something that's easy to factor or find the LCD of. There's a little bit of a glitch along the way. Give me something to do. Look.
Well, I should factor z squared minus 9.
Yeah, I would definitely factor that middle term first. What does that factor into?
Z plus 3, z minus 3.
Okay, difference of 2 squares. Now, you see z plus 3 on the right side, so we'll start by putting that over there, because we know that's there already. So z plus 3 is already there, so what's missing in the right fraction? What's missing in the right fraction that's in the middle fraction? Z minus 3. So I could start by multiplying by z minus 3 over z minus 3 and approach this with method 1. So let's do that first, and then we'll do method 2 in a minute. Okay, let me carry over my original numerators. Notice, look at what I'm putting around everything. What am I doing? What's the word? I have to remember to put around the terms. Parentheses. Okay, the 1 minus 5z is going to be FOILed with z minus 3. So you need the parentheses there. How about the left fraction? What's the deal over there? Because 3 minus z doesn't look like any other factor in there. Or it's not exactly any other factor in there. Nina?
It's negative z plus 3, so then you have to multiply it by z plus 3 times 1 means z minus 3.
Okay, close. Very close. There's an easier shortcut. You could do that, Nina, but that'd be so much more work, so there's an easier way to do it.
Multiply by negative 1 and then multiply it by z plus 3.
Yeah, so you could technically like factor out a negative 1 of that fraction on the bottom left. So take a look at this, please. Write it as Nina supposed first. So write it as negative z plus, z minus 3, write it as. If I do that, if I simply put a negative 1 out front, and I distribute that negative 1 back, take a look, put a negative 1 out here. If I distribute this negative 1, I'm going to get negative z from that, and I'm going to get a positive 3. Well, that's exactly what a minute ago Luca mentioned to take out that negative 1. Now, you said multiply by negative 1. What did you mean by that exactly?
Well, just because it would make it equal to z minus 3.
Okay, so you meant multiply what by negative 1, though? You said multiply it.
The value of 3 minus z.
Okay. All right, so let's use the word factor out. I thought you meant for all the other equations, because what you have really now is this. All right, that's what we have really? So again, I'm rewriting the bottom left fraction as a negative 1 times the quantity z minus 3. I did that because z minus 3 is here, and z minus 3 is here. So I get the same in all three of these. Now the z plus 3 needs to go over here, but this negative 1 needs to go here and here as well. Okay, so what I need to do, let me try and pinch zoom this. There we go. What I need to do is multiply on the left-hand side over here, we're going to have z plus 3, z plus 3. Now, that negative 1 in the middle is a factor. So this is z plus 3 times negative 1 times z minus 3. So multiply negative 1 in both of these now. And you'll have an LCD. What happens as a result? All the denominators are the same. So with method 1, we could cross off all 3 of these denominators now. Why is that? What are we really doing when we cross off all 3 denominators? What are we really doing? Okay, canceling, yeah. But why are we allowed to cancel this? Why are we allowed to cancel?
Because we're all the same.
Because they're all the same. Okay, so what operation will get rid of 3 things that are in the denominator? Multiplication. So technically now, at this point, aren't we multiplying everything by the quantity, and I'm just reading the LCD. Negative 1, z plus 3, z minus 3. We're really multiplying every term by that, and that's what gets rid of it in every denominator. Does that make sense? That's where method 2 comes from. Method 2 comes from that concept that really to get rid of these denominators, you're multiplying through everywhere by those denominators, they cancel. So if you found an LCD to start, and you multiply the original through by the LCD, you would get the same thing as a result. Okay, so we'll do method 2, but for the second example, we'll use method 2. For this one, we'll use this method. So we don't really, cancel these like this, but we can think of it that way. But we're really multiplying through by that LCD. So that leaves behind z plus 3 times z plus 3. I have to FOIL that. Z squared plus 6z plus 9. Then on the middle term here, I'm going to have negative 11z minus 3 equals. Now, how would you do the right-hand side? Because some of you don't always choose the path of least resistance. What does that mean? Sometimes you take roots on the test that are not efficient. And we talk about time a lot, and I keep emphasizing that. A lot of the occurrences when you run out of time is because of the way you rooted yourself to the problem. So what's the easiest way to simplify the right-hand side?
First, you multiply value 1 minus 5z times z minus 3.
I wouldn't do that, no. You could do that. You'd FOIL. All right, so you could FOIL it and then multiply out the negative 1. You could. That is a decent route. But there might be an easier thing to do. If you think about, see the 1 minus 5z? See the 1 minus 5z? I'll point to it right here. If you multiply that by negative 1, doesn't that become 5z minus 1? When you multiply something by negative 1, you're really just switching the order of the subtraction. Okay, and it's not clicking, obviously. 5 minus 3 is 2. 3 minus 5 is negative 2. What do those quantities differ by? A factor of negative 1. So if I distribute a negative 1 to something, and there's a subtraction or a difference in that parentheses, just switch the order. Isn't it so much easier? These tricks are things that you got to pick up on. So I'm trying to explain them to you if you haven't picked up on them by now. So if you multiply negative 1 out, just switch the 5z and the 1. Anytime there's a subtraction of 2 terms, a difference of 2 terms, and you multiply by negative 1, just switch the order. So get rid of the negative 1 and write this as 5z minus 1. And you can get rid of this whole thing here. And then just multiply 5z minus 1 by z minus 3. Okay. How are you? Good. So take that 5z minus 1 and now FOIL that out. It just makes it easier, I think, in the end. I mean, obviously you can multiply out by negative 1. Luke is right. You can do that. But then you might have to reorder things. Your terms are not in order. Now it looks like it's easier to FOIL. So I'm going to get 5z squared. Outer is going to give me negative 15. Inner is going to give me negative 1, making it negative 16. And then last is going to give us a positive 3. At this point in time, you should all be pros at solving this. If you can't solve this, you need to stop and spend time over the next few weeks and revisit quadratics. If you have trouble with things like finding y-intercepts or systems of linear equation solutions, in the next few weeks you need to practice. What did you notice I already put up under documents and handouts? Anyone notice it? Yeah, put up the final exam review document. All it is select questions out of your book to practice. That's all I did. I went through and I picked problems out that are problems that you could expect of difficulty level on the final exam. So as you go through those problems, if you have trouble with them, it means you're not prepared for that topic. You need to come see me and say, you know what, can I spend 10 minutes going over systems? Or, I don't know, inequalities, whatever it may be. Right? But this should be a gimme at this point.
Is there an answer key for the final exam, like documented like practice?
There's not, but all the odds are in the back, and I have all of them in my book. So if you want to know what the number is to check if you're right, just to see, you're welcome to come by. But I want you to come by with your work and show me your work just to see. It wouldn't matter, obviously, but it's not a solution key. It's just an answer key. If you want to go through the problem, if you get it wrong, just go through it. That's fine. But if you want to just come by and look at the textbook, I have the teacher edition. It has all the answers in the back. You can look whenever. Okay? All right. Let's solve this. So let's move the z squared over to the right-hand side, making this a 4z squared. Okay, that gets rid of this one over here. Then I could take the 6z and the negative 11z and make that a negative 5z. And I would add that to the right-hand side, which would make this negative 11z if I add 5z over. It's gone. Then I take the 9 and the negative 3, and that makes that a 6. Oops, positive 6. So I subtract that. Subtracting 6 from this 3 over here makes this a negative 3. And that equals 0. So how would I go about solving this one? What would I have to do? What kind of method? Or what would I do with either AC or quadratic formula? Okay? If you want to see, let's see what we get as an answer. It does factor. 4z, go ahead. Good. Did you use AC or just inspection? Good. Very good. So it makes sense to think about this. So when I was in high school, I only learned factoring by inspection. I never learned AC. My teacher didn't teach it. He would say, all right, look at it. See what the factors are. And I'm like, what? But you know what you have to think about is this could be 4 and 1, right? Or 2 and 2. It's pretty much your only choices for the first terms. I mean, you could have negatives and negatives, but it wouldn't make sense. So you would switch these sides. So 2 and 2 or 4 and 1. At that point then, you say, well, what are the factors of negative 3? It's either 1 and negative 3, negative 3 and 1, negative 1 and positive 3, positive 3 and negative 1. You have 4 options because of the locations they could be in. So there's only like, I don't know, 8 or 16 combinations of that are possible. So if you want to sit there and do your head, you can do it quick. Or you can go AC method or quadratic formula. Okay, but by inspection is great if you can see it. But sometimes some students have more trouble than others with it. So z equals negative 1/4 and z equals 3. Now, are both of these answers correct? Why, yes or no? Are both of these answers correct? Why? Luca.
Well, maybe not because we check if they make the denominator equal 0.
And do that?
What?
Did you check?
Not yet.
Look at the original. It's very easy. By inspection, look at the
Oh,
original.
it can't be 3.
It can't be 3. Look at the original equation. You can't have a 3 and a 0 in the denominator. If you make z 3, and you put that in the original equation, is it one of those denominators, z minus 3 or something like that, right? So it's 3 minus 3. So you cannot have 3 as an answer. What do we call that again?
Just proving it.
Undefined, but what's the term? When we say z cannot be this value, we call it a blank blank. Two-word term. You need to know this term. Domain restriction. Remember, domain is like the answer for an independent variable. Independent variable is like x. I know it says z, but this is an independent variable. This is a domain restriction. Okay, cannot be 3. So the answer is clearly negative 1/4. It also cannot be negative 3, but that didn't come up as an answer. But if I was writing a domain restriction, oops, let me write it this way. All right, the reasoning is because I had z squared minus 9 for the fact that I had a z plus 3 and a z minus 3 in a different denominator. All right. So let's do method 2 same problem again. So for this one, when we get an equation, we'll use method 2. This is not an easy problem. I'm saying it right now. Okay, it's not an easy problem, but there's a way to approach this problem that is very easy. I'm going to describe it and teach it to you, and once I show it to you, if you'd like to memorize the approach, remember for like the mixing problem, for the acid problem on the last test? If you memorize the approach with the table, that's a really, really easy problem. You literally would plug in the title, the amount of milliliters, the percent alcohol as a decimal, or percent acid as a decimal, multiply those two to get a third column, add up the terms to give you the bottom right box. That was literally the same approach. If you did your homework and you did your problems and you got it and you understood it, which I'm hoping most of you did, that problem should have been a gimme. This one is similar in that sense. It's one of those problems, and you're going to see this on the SAT, I guarantee you. It'll be like number 15 or 18, the last one in the section, because it's not easy. But if you memorize this approach, I'm going to show you, it's really actually pretty simple. So, it's the problem where you have two people working on the same job, but they work at different rates. So imagine, how many times have you ever worked with somebody else? I'm hoping everybody has, right? Anybody who has siblings? Raise your hand if you have a sibling, I'm curious. Okay, everybody, awesome. Ever work with your brother or sister? Ever? Think about something. Sometimes it's frustrating. And it's really frustrating when they're being like ignorant and they're like, well, I don't know how to do this. You do it better than me, so I'll just sit here. Or you work with a group member who doesn't really do much for the group, so they play dumb in a sense, like, oh, you know it better than me, so you can do it. And you guys know what I'm saying because you're all in honors classes, so you've probably been in that situation before. So this is the problem where you have some slacker and somebody else who works their butt off. So you talk about rates. So if Luke is working with somebody else who really just doesn't do much, Luca might complete like 10 problems every 30 minutes. 3 minutes a problem. Okay, say they're kind of difficult. Whereas the other partner does like 3 problems in 30 minutes, right? That's what this is. So if you see a problem where you're looking at a combined rate of change of 2 workers or 2 robots or something, that's the approach you want to use. Okay, so let's just preface it with that and we'll begin. Charles, why don't you read it for us?
One spray paint gun can paint a wall in 4 hours in less time than a smaller second spray paint gun. Together, they can paint the wall in 14 hours. How much time would it take for the smaller spray paint gun to paint the wall in 1 hour?
So, we're looking at combined rates here. We have to identify our let statements and our unknowns first. So what are we actually looking for? What are we looking for? Luca?
The rate would be smaller than those.
Not the rate. In the end. You want to re-answer that?
How long it is smaller.
Yeah, how long it takes it. Good. Again, eventually we're really looking into the rate. We're going to look into it. But we're really trying to figure out how much time it would take the smaller spray paint gun to paint the wall by itself. Okay, so let's let that be T, please. Actually, let me think. Let's make that T plus 4. Why am I going to make that T plus 4?
Because you have to add 4 hours for you. 4 hours taken away from you.
Yeah, if I call that other one T, I'm going to have T minus 4. I'd always rather work with addition than subtraction. So it makes sense to use addition instead. So in this case, we see it says 1 spray paint gun, right, can paint a wall 4 hours less time than the smaller spray paint gun. So the smaller spray paint gun takes 4 more hours. So smaller gun time. Larger gun time. Okay? A more powerful spray paint gun takes less time. So T plus 4 represents the less powerful, or the smaller spray paint gun. Alright. Now ask yourself for a moment, if it took the larger spray paint gun, let's pick a number like 5 hours to spray paint the wall. If it took the larger gun 5 hours by itself, the person sitting there using that gun takes them 5 hours. In 1 hour, how much of the wall do they get done? 1/5. What did you say? 20%. Let's take a fraction, but you're absolutely right. And there's a reason, we're picking up on the pattern. If it takes the smaller spray paint gun, then if it took this one 5 hours, it would take this one how long? 9 hours. So after 1 hour, how much of the wall will the smaller spray paint get done? 1/9. 1/5 and 1/9. Agreed after 1 hour? After 2 hours, the larger gun will not be 1/5, but how much fifths of the wall? 2/5. The smaller gun would be how many ninths? 2 ninths. So every successive hour, more of the wall is painted. That is logical, right? Until the whole wall is painted. The whole wall would be equal, would make sense when those fractions add up to what?
45. 1.
To 1.
1.
Because it's a fraction of the wall. Think about it again. After 2 hours, the more powerful gun covers 2/5 of the wall. The other gun covers 2/9 of the wall. 2/5 plus 2/9 is not 1. So they're not there yet. They're not done with the wall. 3/5 plus 3/9 is darn close. It's 0.93333. Because 3/5 is 0.6. 3/9 of a wall is 0.333. 0.6 plus 0.333 is 0.93333. So it's almost after 3 hours that they complete the wall together. You see what I'm going at right now? So, here's how we write that. We're summing two fractions together. We're summing the parts. So part 1 plus part 2 equals whole. This is what I want you to be thinking about. Okay, part 1 plus part 2 equals whole. Well, the one gun in this case, it says here that it takes them together, how long? It says together they can paint the wall in 14 hours. So our numerator is not 1/9 and 1/5. It's not 2/9 and 2/5. Not after 3 hours, so it's not 3/9 and 3/5. It's like 14/9 and 14/5. So our numerator is really 14. Okay, stay with me. It means 14 hours have gone by. Now, what was the denominator the whole time in the example we were doing? The time it took the one robot alone, right? Didn't we say 5 was the number we picked? We said let the more powerful robot take 5 hours to paint the wall. As a result, the weaker robot will take 9 hours to paint the wall, etc., etc. Well, in this case, we're looking at the larger gun as T over here, and the less powerful gun as T plus 4 over here. And these have to add up to 1. Because remember, we don't know how long it takes. I picked 5, didn't I? Didn't I make T5 a minute ago? And when I made T5, I'm making this 5 and this 5, we almost got an answer here as a result. Right? We almost got this to be like a 3 as a result of top. We tried 1 out of 5 and 1 out of 9. We tried 2 out of 5 and 2 out of 9. Well, now, this T is unknown. It's 14 out of the total time. So the easy way to remember this, okay, part 1 plus part 2 is fine, but the way I have written down for students if they want to remember, when it's a combined job problem, do time together, it would take them, which is 14 hours, that was told, took them 14 hours together, over time alone for number 1. And then the time together over here, over what? Over time alone 2. And that has to equal 1. It's always going to work. Okay, if you have 3 people working on this job, it still works. You have 3 fractions that you're going to be adding together. Okay? Again, if you practice a few of these problems, you can even like YouTube or Google the term multi-worker problems, or multiple rate math problems, or completing a job math problems. It's like a classical problem that you're going to see. Anyhow, let's get back to the equation. What would I do with the equation now? I got 14 over t. I'm going to rewrite it. What would I do with this equation? Hold on, what's something else? What would I do to solve this equation? What did we do in the last one? We started with an equation, right? In example 1, we found the what? LCD. Thank you. Come on, we should know this by now, guys. It's all LCD already, right? Everything's LCD. So we used method 1, where we found an LCD for everything, and we canceled the LCDs. Let's use method 2, where we identify the LCD and multiply through by the LCD instead. So what is the LCD?
T times the quantity of T plus 4.
T times the quantity T plus 4. Very good, Kelly. It's obvious because T plus 4 is a factor. T is a factor. So T times the quantity T plus 4 must be it. Why is it not just T plus 4 as a common denominator? Why isn't the common denominator t plus 4? Right?
You can't really add, you can't add denominators together.
Exactly. You cannot add 4 to this denominator and add 4 to the numerator for the 14 over t. You can't say, all right, I'm going to do plus 4 here and put a plus 4 here. You cannot change a fraction by adding something to the top and bottom. That alters the value of the fraction. You have to multiply. So as a result, all we can do is think of these denominators like this. That helps you do this every time. And then that's the LCD. So let's multiply everything by t plus 4. Okay, so I'm multiplying both sides by t plus 4. Well, the right side is easy. It's t squared plus 4t. I'm distributing because I know in a minute I'm going to have to collect terms anyway. The right-hand side is very simple right now. How about the left-hand side? Step me through this, Ben. What do I do here?
You have to distribute the t to t plus 4 and then multiply it.
Good. So when I distribute it to the first term right here, what happens as a result? What do I get?
14t.
Close. What's in the denominator and the numerator there? That cancels in the first term.
T.
T. So what's left behind?
So it's just 14
14, but what else? There's another term there that's still there.
plus 4.
T plus 4?
Yeah.
For the first time you said t. Remember the t cancels. This t cancels. It's 14 times the quantity t plus 4. How about the second one?
The t plus 4 cancels.
Good. Leaving behind?
14t.
Very good. So as a result, we can collect terms now and solve. We got 28, 2 is 56. I'm going to move everything over to the right-hand side. Why? Anybody? So t squared isn't negative. Very good. So as a result, I have a 28t here. I'm going to subtract it from the 4t over here, giving us negative 24t, and then a plus 56. What do I get? Can this be factored? 8 times 7 is 56. No. 14 times 4 is 56. That doesn't add up.
Closest is 2 and 28.
Yeah, and that gives you 26. It doesn't work. All right, so quadratic. So we get 26.1 and 2.1. All right, well, let's use common sense here. Let's use common sense. Together, it takes them how long to paint this wall?
15 hours.
How many hours?
4.8.
So it can't take the smaller gun 2 hours to paint it. Right? Look at this answer. This does not satisfy the context of the problem. How can it take the smaller gun by itself only 2 hours if together it takes them 14 hours, right? It's got to be more than 14, the answer you get. Your domain restriction here is t must be greater than or equal to 14. A lot greater than, really. 26.1. Okay, 26.1 is the time it takes the faster gun. So the smaller gun time is t plus 4, which will give us 30.1 as our final answer. Okay, and my units are in hours. Again, my final answer is 30.1, not 26.1.
Wouldn't that end up being minus 56?
It would. Thank you. Thanks, Ray. Correct this, please, so you don't, because I'm sure you probably got different answers if you use your quadratic program. Then. Thanks, Ray. All right. Other questions on this? Not an easy problem, but the approach is consistent throughout. Okay, here's what I'm thinking. We have one more problem to do. What I'd like you to do is do the written exercises tonight and save the word problems for tomorrow. So written exercises 4 through 28, multiples of 4 for tomorrow. Okay, tomorrow's day 5, right? Yeah. All right. So So I'll see you guys tomorrow.
Thank you, Charles.
Have a good day. Have a good day. Let's see, we have an example here, a boat traveling up and down a river, a distance of 80 kilometers. Due to the current, the speed upstream is only 30 kilometers an hour. What must its speed be on the way downstream for an average of 35 for the entire trip? What's the common mistake here? What's the common mistake? If this is like an SAT problem and somebody gives a quick answer, what do you think they'll give?
To assume that it's 40.
Why?
Because if you average 30 and 40, the average of 30 and 40 is 35.
Yeah. We know the speed on the way up is 30, the speed on the way down. If we assume it to be 40, the average of those two things is 35. Now, how do we know that that's not the right answer? How do you actually know?
Because the speed, or the speed is both upstream and downstream are different.
They are different, you're right. But how do we know that we can't do 30 up and 40 miles an hour down, or kilometers an hour, and that make that an average of 35?
It's 80 kilometer distance. 30 plus 40 is 70.
Okay, but try to think more. Yeah, you'd be 10 kilometers short. Okay, that's one way. Good. I didn't know you were getting it then. There's an easier way though.
It doesn't it's not like 80 kilometers split in half, it's not 40-40. You don't know when you're going to turn around.
Yeah, you're not doing the same time period in each direction. So for example, if I travel 30 kilometers an hour for half of a trip, and then I travel 40 kilometers an hour for the other half of the trip, it takes me a lot more time on the first half of the trip than it does on the second half of the trip. Now, if instead of a distance, this is like upstream at one rate, downstream at the other rate. Instead, if I were driving from New York to, let's say New York to Philly, and let's assume it's 200 miles. If I drove the first 100 miles, and then a different 100 miles at a different rate, averages the average of 2. But instead, if I drove a time period at one rate, and a time period at the other rate, we could use that average. So what we're going to see here is we're going to use our distance rate equation. And we're going to have three parts of this. So think of this as three legs of the trip. Okay, so let's go. And one of your examples in your problem set had to do with,
Running uphill and down.
what was it?
Running uphill and down.
Yeah, it was like two legs of a race or running in two parts. And we also did one in the past where we had two objects that were moving toward each other or two objects moving away from each other with distance rate. Not much more difficult, but break it up into segments. There was also one with an elevator. The elevator went up, paused at the top, and then came back down. It's a distance rate problem. They're all distance rate problems, really, these. What do we do for the first part of the race? Or boat travel, whatever trip. From here to here. What do I label from there to there? 30 kilometers an hour, okay. And what does that represent? My what?
The amount of time spent going upstream.
No. The what?
Speed.
The speed going upstream. Thank you. The rate. Remember, time is t. That's in measured in hours. Look at the units. Kilometers per hour, right? What else?
Your distance would be 40 kilometers.
And the distance is 40 kilometers. What else can I label? Right? I think I Okay, D total is? D total is 80, good, in the problem. So therefore D2 must also be 40. Anything else? Come on, there's something else, guys.
Well, you can make your second rate x.
Make the second rate x, all right, that works. It's unknown. What else?
120 over t plus second rate over t all divided by 2 equals 35.
All right, so let's label other things, though, still. There's more to go, guys. You're jumping the gun. Way ahead again. Answer questions that are asked. There's something else that's missing. You need this last piece. Without this last piece, you can't make this easy. is a simple way to solve this if we can label one more thing. Mike?
Is it like 30 minus x?
Not 30 minus x? Physically, look at the problem. There's a number you have not stated. This is not difficult to make that statement. Nina?
35 kilometers per hour is your average.
Is the average velocity. Now, where does that go is the hard question. Kelly?
30 plus x over 2 equals 35.
No. If that was true, then the answer would just be 40, as he stated in the beginning. Right? If 30 plus x over 2 equaled 35, you're saying the average, right? And we said in the beginning it's not the average. That was the whole statement.
Since you know the formula that rate times time equals distance, you know that 35 would be multiplied by the total time, which we don't know yet.
Which would give us the what?
Which would give us the speed of the second, the way down.
No.
The total time spent.
It wouldn't give us the total time spent. Again, her statement was, if you take 35 miles an hour, or kilometers an hour, multiply it by the total time, you get, what do you get?
Oh, as a total distance.
The total distance you would get. The average velocity of an entire trip times the time of the entire trip should give you the total distance, because it's an average velocity of the whole trip. So let's put this down here as our bar for average, or AVG, whatever you want to call it. A bar over it in physics usually means average or constant rate. So we'll say that the average rate here, again, is 35 kilometers per hour. So we really have this, ready? We've got one piece of the puzzle here. We've got another piece of the puzzle up here. And another piece of the puzzle right here. This is what I keep saying to you guys. It's not a problem where you can just say, Mr. Howell, how do I do this every time? This is a distance rate problem. We've seen like 30 distance rates, but it's different, right? You have to adapt as the problem presents itself. So we've done ones, at least 3 or 4 this year at least, where there's pieces to the problem. There's the first leg of the trip, the second leg of the trip, or somehow something pauses in the middle, or 2 runners are running in opposite directions, but there's multiple pieces to every problem. Your hardest part is to identify those 3 pieces. What do those 3 pieces all have that is missing? What is it?
Time.
Time. Where's time? Is time anywhere here? It's not. So that means that we probably need to get rid of time somehow. How can I get rid of time? And this is really tough to understand. It's not easy to pick up on right away. How can I get rid of the time in each scenario?
Make time the denominator and columns. Like if you
That's a good approach. Have time in the denominator, maybe multiply through, but it would end up in the numerator still. But that's a good approach. I like what you're saying to get rid of it. What else?
Well, time equals distance over rate, so if you have the rate and the distance for one, and you have x as a variable for the other, you can find t1 and t2, and then add them to get the total.
Yeah, so there's another equation at the end. Say it one more time, the last part.
If you add the 2 times, then you'll get the total time, and then you can multiply it again.
Yeah, so let's write that as a statement what Nina just said. The time it takes in the beginning, we would call that T1. The time it takes for the second leg of the trip would be T2. And that would equal the total time. So by writing this equation out, we've enabled ourselves, or we've given ourselves a way to substitute in for each of those T's and as a result get rid of them. How can I substitute in? Well, write out your distance rate equation. Your distance rate equation is D equals RT. I'm going to write it, here, hold on, I'll move over. I'm going to write it in green on the left. Okay, distance equals rate times time. So if I solve for time, time is represented by distance over rate. If that's true, you can replace these with distance over rate. Distance over rate. Distance over rate. Okay, so I'm literally replacing all of the times with distance over rate. And as a result, where do the times go? They're gone. We don't need them anymore. So the key to this kind of a problem is to identify that you have, and it's not obvious to see this, 4 unknown variables. The 4 unknown variables are R2, T1, T2, and T total. But how many equations do you have? careful.
You have 2.
Is it 3 equations?
1.
Because you 4.
Why? You're close. Why?
There's 4 because there's 1 which you gotta do. You have to solve for the times. So that'd be the one on the bottom.
This one over here or which one?
We have to find the average speed. Well, I can't explain it properly.
Who can explain it? There's clearly 4 unknown variables in this problem. R2 is unknown. T1, T2, and T total are also unknown. How can I solve a system when there's 4 unknown variables? I need 4 equations. That's why you're right with 4, but there's a reasoning behind it. Look at this scenario. This scenario tells me T total equals D total over R bar. This scenario here in the middle tells me T2 equals D2 over R2. That's the second equation. The top scenario tells me T1 equals D1 over R1. That's what I'm placing in these 3 spots. These equations here, it looks like one equation has been replaced. This is the 4th equation right here. So what you're really doing is this. You're taking this equation 3 times, once for each scenario. Here's the 4th equation right here. So as a result, if you take the equation d over r for all 3 of these, d over r, d over r, d over r, and plug them all in to the 4th equation, it gets rid of 3 of our unknown variables. It's not a coincidence that this worked out. It's kind of a problem where you have several legs of a trip and you're looking at rates. You always want to use this method of T1 plus T2 equals T total. Remember with the washer yesterday? I gave you a generic method for that. And I said it was like time together over time alone. Plus time together over time alone for the second machine. The paint problem, yeah, equals 1. And I said for a multi-purpose problem, it's a very easy thing to remember. You can remember this, okay? Or you can just understand the problem and think about that you have 2 legs of a trip. The only thing that you could sum together are the times. Okay, the times add up. The reason I do that is because there's nothing known about time here. I'll grade that last problem very easily, okay, for the test. So again, for these 2 values, we want to get rid of them. That's why we're using this. Had I not known distances, had I known all the times, here's what I would have done. Had I not known distances, I would have called this D1 plus D2 equals D total. And maybe I knew the times. And it wasn't a round trip. Make believe it was like a sailor goes from point A to point B.
Wait, like
say an unknown distance, but for 3 hours. Then from B to C for 7 hours, another unknown distance. And then you get all the rates and the other stuff, but you don't know the distances now, but you know the times, right? You could say D1 plus D2 equals D total to cancel out the distances, so you don't have them in the problem anymore. So depending on the problem, because we didn't know time here, we use this as our last equation. Let me explain what I mean as an example. I'll do another example after this. So let's plug in what we know here in this last equation. So D1 is 40 over R1, which is 30, plus D2, which is 40, over the unknown R2, plus a total over the average. Okay? So this is our equation. This is not the equation you would suspect just by analyzing and looking at this problem. It's not a problem where you're going to just look at it and be like, oh, I'll come up with this equation. It's really simple. Okay, this is not a simple thing to come up with, the idea or the concept behind it. So what are we going to get as a result here?
16/7.
What do you got?
Well, 80's 35th simple class is 16 seconds, which is 2 hours and 2 seconds.
And I want to solve for x. What should I do to make this easy on myself? How do I solve for x?
You have to get a common denominator.
Which is?
Well, you could either do 21x or 3x, depending on. I guess do 21.
I'll do 21x to clear them all out. So what do you got when you do 21 extras?
That'd be 28x over.
Reduce them first.
Sorry. So 40 for x over 3.
No, reduce, man.
84.
It's Stop, pause. Reduce, watch. 21 over 3 is 7, isn't it? So 7 times 4 is 28x. And take 21 over that x right there. Well, the 21 times the 40 we're going to have to actually multiply out, right? So we're going to get 840. Now the x's are going to cancel in this case. This x cancels with this x here. And then reduce again. Giving us 20x equals 840. What are we going to get for x here? 42. Now, what was the answer that we suspected would be the common mistake? 40, because the average of 30 and 40 is definitely 35. So explain this answer now. Explain this answer in physics or in like everyday like terms, meaning like using real words and the scenario itself, not just math, but explain it having to do with the scenario.
Won't you like automatically go kind of faster if you're going like downstream?
Oh, absolutely, but explain how this works out to be the average of 35. You're definitely going faster when you're going downstream. Absolutely. We knew that though, because the average was 35, you have to be going faster.
Well, you're absolutely, because of the average number we had before, it had to be over 40 because
Why?
when you spend more time going up, you need a higher number to get it to 35.
Yes. That is the key. So let's think about this again. If you travel slower on the way upstream, slower rate, 30 kilometers an hour, isn't that going to take you longer to do that? So it's a weighted average. That's what this is. You don't spend half the trip up and half the trip down. You spend most of the trip, more of the trip on the way up than you do on the way down. Because on the way down, you're going faster. When you travel faster over a certain distance, it takes you less time. So the value of that number, 40, has not the same, it does not have the same effect as a 30 does then. The 30 is for a longer time period. So as a result, on the way down, you have to compensate for that longer time period on the way up with a higher average velocity on the way down. Again, it's not 40 because 30 and 40, you'd have to be going for the same time periods. You're not. It's taking you longer on the way up, which means that you're traveling for a longer time at a low rate. It would be like this. Imagine your first 2 quarters of the school year, you get an 85. And you want to get an average of a 90. And after the 3rd quarter, you say, okay, so I have an 85, and I want a 90, so all I need is a 95 in the 3rd quarter. Why isn't that true? Why isn't it true that if you get an 85 the first 2 quarters, giving you an 85 average, why can't you just get a 95 and average would be 90? Why is that not true?
You need 95 in the 3rd and 4th quarter. Because then it'll average out to 90.
Why then?
Because 85 plus 85 plus 95 won't make it 90, it'll be lower.
So why? Because you're doing what? You're absolutely right, mathematically. Give me more of like a...
You're spending more time on the first 2 quarters?
Yeah, the weighting of the first 2 quarters is 2 of your frequency elements. The 3rd quarter is only 1 of them. The first 2 have more of a weighting together, right? They have 2/3 weighting out of 3. Same thing here. You spend more time on the way upstream, so the 30 kilometers an hour has more of a weighting. So you can't equally weight that with 40 to give you 35. So you need to compensate for that. So you know your velocity should be greater than 40. 42 is our answer. Okay, so you need to make sense of your answers. Sometimes I see answers, and I look at them and I say, did you really think about that afterward? So if you have something that's not reasonable, try and figure out what went wrong along the way. Okay, and I don't always mean that with tests, because tests I know you're always impressed for time on tests. But for like problem sets and stuff, if you make mistakes in that or any of your homeworks, think about those. Make sure your answer has some logical reasoning. So let's do a problem again like this. I'm going to add a problem, okay? So add a new slide. And what I'm going to do is, but instead of unknowing time, we're going to have unknown distance this time, okay? So it's going to be the same approach though, right? We can all see that it's going to be the same approach. So let's say that you're traveling upstream or you're traveling from point A to B. Let's use A to B and make it easier. Traveling from A to B for 2 hours. At a rate, I would recommend writing the words, by the way. I'm drawing the diagram, I'll explain it. But I recommend writing the words when you study the words are there. You're traveling from A to B for 2 hours at a rate of 30 miles per hour, or let's say 40 miles per hour. Then you detour to get to point C. I'm doing that on purpose. We don't know the distance, okay? It doesn't matter what path we take here. To get from B to C, you take some detour, some side route, and that takes you 3.5 hours. You go at an unknown rate during that second leg of the trip. If your average velocity on the trip, or average rate on the trip, ends up being I want to make this interesting. 37 miles per hour. Determine the rate during the second leg of the trip. Determine the rate in the second leg of the trip. Now, you could do this as a weighting, and you could probably do it. Let's do it with distance equations. But you can definitely do this as a weighted average. If you know your math well enough, you can probably figure it out in your head. Let's look at this as a distance rate problem then. So in the beginning of the trip, we know d equals RT for the beginning. For the second part of the trip, we have d2 equals R2 times t2. And for the third leg of the trip, we have d total equals R bar times t total. What is t total? What is t total? How much? 5.5 hours. All Ryan did was add the first two times together. There's situation 1, 2, and 3. Okay, there's our three situations. Now, we clearly have three formulas we're going to use. 1, 2, 3. The problem right now is we have 4 unknowns. We have 4 unknowns. What can we write as the last equation to make it simple for us? Think back to the last example and relate it to this one. Think back to the last example and relate it to this one. What's the last thing I could write if I want to? Right? Because look, clearly, guys, watch. We could find this distance easily, right? R times t. We could find this distance easily, R times t. But right here, we're missing the rate, so we can't find this distance. What should we do?
So it would be 40 over...
Give me an equation, please. Come on.
First you need to figure... I'm thinking this wrong, but first you need to figure out the equation already. It has to be d1 over r1 plus d... No.
Making it too hard on yourself. Come on, last time we had T1 plus T2 equals T total. Agreed? Would that do us any purpose here at all? No. So think about how you can change that. Instead of time, what could you use there? Yeah, use distance. What would it be? I mean, that's all we're doing here, guys. Because look, if you have the RT from the first one, RT from the second one, you're missing R from the third one. Put this in here, you know both. Put this in here, you know both. Put this in here, you're missing R2, solve for R2. You could also have determined the distances, subtracted those two distances, and set it equal to distance 2. Right, watch. What's the total distance? 5.5 times 37, that's the total distance. What's the first distance? 40 times 2. Take this distance here, subtract this distance, well that equals D2, then divide that by the time 3.5 hours to give you R2. You can do this by inspection or just write it this way, and it's more obvious this way. So we've got 40 times 2 in the first one, so this is going to be R1 T1 plus R2 T2 equals R bar T total. As a result, we're going to have 40 times 2 plus R2, which is unknown, times 3.5 equals 37 times 5.5, not that it matters. Okay? And physically, if you look at the numbers, that's what I was just telling you. Like, look, this is the total distance on the right. Subtract off the first distance. It'll give you what's left of the second distance. That's the number we're going to get. And divide it by time to get R2. Okay, what do you get for R2? What do you get for R2 when you solve this?
35.28.
What is it?
35.28.
35.28. Make sense of our answer again. Our average was 37. Our average was 37. The initial velocity was 40, or the velocity on the way there. So this being 34 would be exactly even, but we know it's not. So R2 is not 34. It's more than 34. Why? Because you're spending more time on it. Okay, you're spending more time there. So again, we're looking at a weighted average each time. I'll be nice again with the grading on that last problem. Okay? I assumed it'd be a little bit easier, and I probably put these two sections together last year, so I had those problems in my mind for the same section. Written exercises. Easy last night? Any questions on that stuff? Yeah, pretty easy? No, yes, maybe? Over the weekend, what do you have to do? Okay, there's like 4 word problems in this section. Alright, so again, last night you did this right here. So over the weekend, do this, please.